15-second mark.
3, 2, 1, and liftoff.
Dragon is in orbit.
I'll introduce a little bit about edible insects and EntoCube in general, and then I'll dive into how all this fits into the Mars missions in the near future. So let's get started with that. So yeah, I'm a civil engineer, graduated from Aalto University last year. I've had a very keen interest in space since I was a kid, and back in 2000, I believe 12, I became an astronaut candidate in the International Mars One project, and that's a long story, how I became involved in that and what transpired during that process. During that time, I also worked at a big international engineering company, Pöyry. I've also been a medical sergeant in the Finnish Defense Forces. So I have a medical background and a civil engineering background, especially to do with geotechnical engineering, and that's to do with rocks, soil, and how to engineer those into infrastructure, foundations, and such things for human habitation. And as we know, on Mars, there's pretty much nothing else right now than sand and rocks. So that's kind of is also an area of my keen interest. But yeah, to dive into the space side of things, I was thinking that you could show the first video, which is my application video for Mars One back in 2013, I think. So if you could play that, and we kind of get the feel for how this all began.
About a year ago, when I first landed with Mars One, I've thought about this every day. And every single day, I find that I want it more and more. I've come to realize what I would be stepping into, I truly have, and I've come to terms with the realities. All I want is to dedicate this one life I have to something truly meaningful. What I've built here on Earth is something great, but I see the opportunity to build something even greater, something far beyond me or any individual. If I'm ultimately selected, I am willing and able to commit myself to this life, wholeheartedly. And I'm in it for the life, not just another experience. My sense of humor is just very appropriate in any situation and role. I'm very mature for my age and prone to self-reflection. Finding a common sense of humor has never been an issue with most people, and people find it very easy to confide in me for some reason. And there's a lot of things I'm not, but I am a family member and a life partner.
So yeah, I mean, going back to the Mars One story, I mean, it's a long story. Many of you may know that it's a one-way trip and all that jazz. But during that time, when I was an applicant and I talked to the people there, I did some voluntary work for them. For example, some studies on geotechnical engineering to do with radiation shielding of the inflatable living units, and in specifically how to bury them under 5 meters of sand or regolith as is it in Mars, and radiation shield those astronauts there. And I looked at their case, their current design, and I designed them a new version that could possibly be used. So I sent that material to Anna. If you want to look at it, make good use of it. Also, some other geotechnical applications I came up with during that time that may be of use to you guys, maybe even to the other groups that are not right now here in the room. But feel free to use any of those ideas. There's a lot of opportunities you can do on Mars that you can implement then on Earth commercially. So yeah, too few people realize how many applications are useful also on Earth commercially and on Mars. So make good use of those. So yeah, I mean, there was news back in the day, I think 14 or early 2014, press was saying that 5 Finns selected for this trip. I was one of them. I was anonymous at that point, and I wanted to keep it that way. I was not so much in disagreement with the one-way trip aspect of things, but I was in disagreement how Mars One conducted their business, so I dropped out eventually, and that's how I went more forward with things. But during that time, when I was in Mars One and trained and prepared, I realized that one of the key challenges in going to Mars is not only landing, as SpaceX is doing, but also sustainable food production. So those two are the key challenges to be solved in the near future if we want to go there. And as we looked into this side of things, sustainable food production, it became clear that insects are going to be one key component of the solution. And that's how I was introduced to insects. And if you look at the bigger picture, it's sustainable food production. It's not only a problem for Mars, it's a key challenge also here on Earth. So right here at home, access to food, climate change, all these things that are intertwined are, fundamentally, they all begin with how we produce food. And right now, it's not on a sustainable base. So we need to find a solution for our food production here at home. So if we look at the situation now, by 2050, we're looking at 9 to 10 billion people, and we're looking at producing twice as much food as we are producing right now, and that's only 35 years away. And the thing there is that it's not only to do with population growth, but the poor people in developing countries, they're being lifted from poverty, which is really good. But the thing there is that the more rich you are, anywhere in the world you are, you're going to eat more protein. And how we produce protein right now is not sustainable at all. The amount of land we use, the amount of water, energy, feed, these are all on a very unsustainable base right now with how we produce our animal protein. And back in 2013, I believe, it was the United Nations, FAO, that came out with this report, which is pretty much kind of the Bible of the edible insect industry right now, that said that edible insects are going to be the solution to this protein problem, this food crisis that we're not only going to be facing, but we're facing right now in different parts of the world. And so if you look at, here's a comparison of the environmental, the production benefits of insects. So if you compare, for example, cattle on the top and one insect species, the cricket, on the bottom, it's a whole different world, where we're at, how efficient it is, how sustainable it is. Compared to cattle, crickets are, up to 5 times more efficient in feed use, up to 2,000 times use less water, and 1% of the CO2 emissions, essentially. And a fraction of the land, to mention that too. And there's also other benefits that you can use food waste on top of things to feed insects, and that is a feed source that is really untapped right now, because about 30 to 50% of all global food production is right now going to landfills and not being used, to feed people or animals. So that's an untapped potential right there. So if you look at edible insects worldwide, they're consumed by 80% of people. That's about 2 billion people that use it as a staple food daily, and that's mostly in Southeast Asia, Africa, and Latin America. So Europe and North America are pretty much the only places that are not very familiar with this, but that's changing. That's changing. And if you look at what can you do with this, do with these edible insects, traditionally in these developing countries they might be eaten whole, but there's a lot of other things you can do with them. So you can eat them whole, you can grind them into ground up meat, so make like burger patties, essentially burgers. Then you can do, cricket powder, insect powder. That's pretty much 70% protein, and it's got iron, it's got calcium, B12s, it's got a lot of good things. That powder, and you can bake it into these different goods that already look like what we eat, whether it's cakes, bread, chocolate, smoothies, whatever it is. But you can consume insects in an unrecognizable form. So that's what we believe is going to be the future in the West. And here are some statistics on what the nutritional content of crickets are compared to other insects, and also chicken, beef, and fish on the bottom. So a comparable amount of protein, and it's much more rich in some other vital nutrients here. Calcium, iron, and B12s are probably the most notable ones here. And you can perhaps look at that as you get the slide. And if you, that was whole. This is when you grind it down to powder. So it's highly nutritious. It contains all the essential amino acids, for example, cricket powder. So it's really a superfood in the real sense of the word. Here are some commercial products that are already available in the West. Pancakes, cricket pasta, shakes, protein bars, buns, cookies, even bitters for drinks. A lot of different things they can do with it. And the market potential is really awesome. Right now it's about 360 million euros worldwide, the market size, and that's about even of Asia, Europe, and North America. And this is whole insects. But the bigger potential is insects as an ingredient. So the dry powder that I was talking about. So that you can bake into anything. So markets are huge. Then coming back to the story of EntoCube. So I got the idea of insects. I was introduced to the idea of insects through this experience as an astronaut candidate, as I said. Then as I was working as a civil engineer one day at a construction site, I came across this office container. It was dead middle of winter, and I went into this office container, and I realized that you can actually live in these things year-round. It's warm inside. So that was when I kind of put one and one together and realized that you can take these insects, put them in the shipping container, and in these shipping containers you can rear them, year-round, anywhere in the world. And shipping container units are available everywhere in the world. So that's how the idea came into fruition. But that was, I think, 2014. That summer, I took some vacation off from my work, built the first prototype shipping container unit with my father in Vantaa, and I started, trying it out. Didn't really have that big plans at that point, but later that year, it was the Helsinki City Marathon that I ran that really got things started. I ran with my friend Henry, and he got in front of me. And at the 36-kilometer mark, I came across this corner, and I saw this man lying down on the pavement. Runners were helping him, some bystanders were helping him, and I didn't see the guy. I didn't see who it was, and I ran past him. I thought he was a heated, stroke, and other people would take care of it. I was just so focused on my own thing, getting a good time. But I was a medical sergeant in the army. I could have helped. Afterwards, a few weeks later, I heard that the guy on the marathon was Henry, and he had died right there on the spot. So after that, I made a solemn promise to myself to never, ever again run by. If I can help with something, if I can, be of influence to make a positive change, I'm gonna do it, no matter how hard it is, no matter circumstances. If I can help, I will help. If I have the ability to do something, I will help. So that was how the EntoCube business started going forward. But then, okay, so if 80% of people already eat insects across the world, so why aren't these present in our current diet? I guess that's the question, right? So how they're farmed, or rather collected right now across the world, most places, it's like they have people going to meadows with nets. They gather it from nature, and so right now it's really seasonal, the availability of insects. So you may have a month in the springtime and a month maybe in the autumn time when the temperatures and the conditions are really perfect for the insects, and that's when you collect the insects from nature. But otherwise, in the summer it's too hot, in the winter it's too cold, and so these people who may rely on insects as a source of income just have these really short periods of time they can practice their craft there. And also people who rely on this food as a protein source only have those short periods of time they can collect it. So you need a farming method that is more reliable than it is now, and controllable. And so that's how we started to figure out this EntoCube business. And what we came up with, well, I guess we can, this just goes to show that the industry right now is really underdeveloped. So if you have the farmers here on the left, technology providers, then logistics, we've got processing, and then the retail shops, all of this has to come together to make this industry a working environment. And right now, EntoCube is in a lot of different places, unfortunately, because the industry is so scattered, so underdeveloped. So we're looking into including big partners, small partners, to kind of put our focus more into the technology side of things. So that's where we want to be, in the production category here. But I guess we could roll the video. Hey, yeah, Anna, roll the second video right now. So that's the EntoCube promo video.
Eating is universal, but what we eat really isn't. I mean, insects. Now that's a good source for protein.
Did you know that we actually grew these ourselves?
I didn't.
Yeah. Would you like to know how we grow these?
Yeah.
Okay, let's go.
It all starts from here. A lot of food waste is happening. Right now we're at Taffa, a student restaurant in Otaniemi. Earlier all of this would have been thrown away, and now thousands of crickets can feast on this.
This is the EntoCube, and this is where the crickets grow up. It's a standalone farm, easy for anybody to use. It can produce up to 10,000 crickets a day. That's enough to feed 10 people.
We are going to revolutionize the way food is produced in urban environments. With an EntoCube, you can produce food in places previously thought impossible. Since the cube can feed so many, it brings entire communities together. Did you know that cricket powder is 68% protein? It's 20 times more efficient than cattle, and in fact, 2 billion people already eat it as a part of their diet. We love the taste of crickets, but what do other people think?
Tastes like chicken.
It tastes like chicken. Mä voisin leikata katkarapua. Näyttää hyvää. Katkarapu. Joo.
So let's summarize. The EntoCube is a standalone unit that can mass produce protein anywhere in the world. It produces insects. They're easy to grow and they contain all the essential amino acids, plus they're really high in iron and B vitamins, essential nutrients. With the EntoCube, we can revolutionize food production globally. And to do this, we need your help. Please help create the buzz by sharing this video, please like our Facebook page, and please stay tuned because there's a lot more to come.
Okay, so you saw a little of how it looks. So yeah, I mean, coming back to why we created EntoCube, the shipping container unit. So right now, there's, for example, in Thailand, there's 20,000 cricket farms already, but it's pretty much only manual work. They have a box, they remove the box, they feed it by hand. It's really manually intensive labor. And so that keeps the price high of insect protein, and it also makes it not so scalable, and there's a lot of different drawbacks in that. And with climate change, with these farms that are now in Southeast Asia, for example, they're all outdoors. So climate change brings some challenges because the temperatures vary, and insects are very prone to the differences in temperature and conditions. So we came up with EntoCube, which is an environmentally controlled shipping container unit where we can control the variables very precisely. There we can have a system that is really scalable. So we can have 1 container, 2, 3, 4, or 5, or when we go into factory level production, we can strip down that metal shell and essentially have that module again multiplied in the factory scale. And that makes it really, technologically scalable, even in the West. And we can apply automation and all that jazz. And so here are some stats. For example, for a 20-foot shipping container unit, it's insulated. For example, in the wintertime in Finland, you really need insulation. So it's about 30 degrees Celsius in there, even more. It's a really humid environment. We control the CO2 as well. And then we get a certain output of crickets every single day. So it's this cyclical system where everything with the life cycle of crickets happens inside the shipping container unit. And we get every day something out, which we then free store and then use for different products that we now sell in stores in Finland. And then there was a question I got from Anna about environmental, how important is the environmental system to the growth of cricket. So I added this slide. So it is very important. Temperature is the key to insects, especially the crickets that we rear. So if, for example, we would do this in room temperature, we would get about 3 harvests a year, maybe. And now that we are in a shipping container unit where we can control the temperature and get it up to 30 and even more, we can get a lot more harvests during the year. So it's much more efficient. It's much more, we can monitor it in a much more efficient way. And yeah, EntoCube, we do the shipping container units, but then now we're turning into industrial solutions where we do this scale up version of what we would have inside the shipping container unit, but in much bigger scale. And then we also sell, consumer products. We have Sirkkapurkki now in stores, for example, in 5 different locations. So that's well, we say it's a decoration, but it's hopefully in the future it'll be a food product people can buy under that name. And yeah, from these single units to really mega factory scale, and we're developing that automation, those production solutions, those data collection methods that would have to be in place to make that automation and big scale production possible. So that's what we're doing every single day, doing the technology side of things. All right, so then we come to Mars. So how do we implement all of this into the context of colonizing Mars and making sustainable food production there possible? So yeah, so last year we did some cooperation with BioMars from the NASA Epic Challenge. We've been in some contact with also ESA, which have the Melissa program. That's a pretty nice developed program. You should look into it if you haven't already. And I could explain this. So when you go and implement and take edible insects and feed insects to Mars, here are the steps. So before you take a flight and go anywhere, you have to have the right insect species. So what you need to know about insects is that there's right now about 2,000 different edible insect species across the world already. And they're used either for human food or then animal feed. So those species are different for each case. And what you need to know is that a lot of these insect species are very traditional. There's not a lot of scientific research on them. So there's a small array of insect species where you really have, scientific information and you really know what they're all about in detail. And I would say that when you choose a species for a Mars mission, you would want to go with these well-known insect species. You have decades of information already available, you have decades of experience in using them as staple food for people and feed for animals. So you need that history and that testing. So that really narrows down the possible insect species you can use. And so here are, for example, 4 species pictured that could be possibly considered. The cricket that, for example, we rear ourselves, the mealworm, and then the black shoulder fly. Here, the 4th silkworm popeye. Those I put here as an example of, well, the Chinese have considered this silkworm popeye as something they could take to space. But, for example, one of the considerations when you choose an insect species is that what do they eat? In the case of silkworm popeye, they only eat a specific type of tree leaf. So they don't eat just everything. So one of the considerations here on the right is that you want to choose an insect species that eats pretty much anything. And so that gives you versatility. And then there's, of course, the food criteria here in the middle, that you really want a tasty food. You need it to be a versatile food ingredient. So you don't want astronauts to eat just one thing and get bored with their food. You want to keep it, interesting and enable a lot of different recipes. So that's why I would say that crickets and mealworms here are definitely the way to go when you go down that route of choosing food insects. The black soldier flies is more for the animal feed. So when you've chosen the species, the right species, then you have to get those insects to Mars, right? So there's a lot of different challenges, some of which overlap with the challenges we face with human astronauts as we send them to microgravity and beyond our orbit, which is of course that the trip takes a lot of time, up to 6 to 9 months to Mars. You've got a limited amount of space available to you. Supplies are in low demand, and you have to take care of all these different aspects to do with environmental control and all these different things. So here are a couple solutions to take insects to Mars. I would really go with the first option here, that you forget rearing insects during microgravity flight to Mars. So you would take frozen eggs on Earth, put them in a radiation shielded safe, and take that safe full of eggs then to Mars. So that way you wouldn't have to figure out what you feed the insects during the trip. You wouldn't have to have these insects up on astronauts' faces. That's gonna get real cramped up and creepy. So I would really freeze the eggs. And there's precedent. If you think about it, every year in Finnish conditions, for example, insects overwinter about the same period of time as the trip to Mars takes. So the winter here is about six months maybe, and so the insects have to survive by lowering their metabolism and overwintering, and that way there are insect species that naturally do this kind of overwintering over this kind of period of time. And then when you get to Mars, then you thaw the eggs and get the production going on that end. And then at that point you'll have plant crops which you can feed the insects as well as feed. So that all works out well. Option 2 and 3 would then be that you forget the eggs and then you actually farm live moving insects in space with the crew, and that would be a whole other different ball game. which has been done. You know, there's been tests in the 80s, for example, with insects, and even in the 90s, where they've successfully, you know, reared bees, honeybees, crickets, moths, and other insects. So it's possible, but there's a lot of challenges. And yeah, well, this was one consideration actually from BioMars, this automation. So I believe NASA has the plan of first sending, you know, unmanned missions to Mars, and with automation, with robotics, you would set up the whole farming ecosystem, the whole habitat, before any crew arrives. So any system, food production system you put in place has to have a level of automation, and that is actually what we're developing, you know, automation for insect rearing. So that goes well together with that plan. Once you're on Mars, you got the insect eggs, you want to start farming. So what happens then? How do you set up this whole farm? So first of all, you know, insects don't grow on, you know, nothing. You need inputs, you know, water, feed, heat, that kind of stuff. So first you have to get your plant crops up and running, whether it's a potato farm or salads or whatever it is. And then you use the inedible plant parts from that to feed the crickets or mealworms or whatever the insect species is. And you have to have a certain level of automation to you know, save time from the crew to do more essential stuff and take the human error side of things away from the equation there. And then yeah, there's this cyclical system versus batch system. So there's two ways of rearing insects. Cyclical system means that in your certain sized population of cricket, for example, you have all age groups from, you know, newborns all the way to adults and all the eggs. So you have all the different age groups, and you're doing the cyclical system where you're getting, you know, certain input all the time. The batch system is where you have you know, just one aged crickets, for example. So you have a lot of eggs, and all those mature at the same rate, and then you end up with a big harvest. But you don't want that in the context of Mars. You really want the cyclical system where you can maintain the system all the time. Because in the batch system, you need eggs from somewhere. And on Mars, you wouldn't get that from other farms. You have to be very independent with that. Yeah, so some steps, you know, roll out the system. As you saw in the video, we have some plastic boxes, but we're developing other methods as well. You know, nylon bags, roof rails, nets, different kind of surface materials we're testing. There's a lot of different ways you can rear insects, especially crickets. And what else here? Yeah, once you get the frozen eggs from the spacecraft, you want to thaw the eggs in different batches. So you hatch one group of eggs at one time, the next day another batch, and that's how you get the cyclical system in place on the Mars side of things. And then there's some things you need to automate here. And the automation systems that we're developing here on Earth are, I would say, directly implementable here for the Mars colony. So automation of different production solutions and automation of you know, handling the crickets themselves. Here on the left, we have the ESA Melissa way of doing the closed loop life support system. So here essentially how it works out is that you got the crew and they produce some, you know, human waste, and then also on the you got some inedible plant parts, you know, roots and such things, and you put those two waste streams into a compartment, which is essentially a bioreactor, and then you kind of take it to bioreactor 2 on the bottom, bioreactor 3 there, and then what you essentially do is you extract the nitrogen and you extract the minerals from these waste streams, and you give it to the plants as a fertilizer, and then the plants produce food to the crew. So that's essentially how the cyclical system works. So here on the right, you got an alternative system with edible insects and also feed insects. So if you look at just the food insect cycle, again, you got the crew. And well, okay, let's start with actually the inedible plant parts on the top. So you take the roots, you take the food waste, and you feed it to food insects. So those food insects could be crickets, they could be mealworms. They pretty much eat anything, those insects. So those are fine food for them. So then the crickets grow, the mealworms grow, those become food for the crew. You get the protein, you get the all essential amino acids, B12s, iron, calcium, all the good stuff. Also, with the food insects, you get droppings, a lot of it. So that's essentially organic fertilizer that you can then use to grow the plants. And already now, cricket droppings are used as a commercial organic fertilizer in the United States with the name cricket poo. So it's got really good values as an organic fertilizer. And if you want to take it to the next level, you can use, for example, the crew or waste to feed another type of insect, feed insect, black soldier fly. And those are reared commercially with livestock poo here already on Earth. And those you really don't want to feed to the crew themselves because of what they're being fed. But for example, you can feed them to fish. And if you have an aquaculture system in place in this food production system, you can then get feed for the fish, and then the fish provide food for the crew. And all this results in reducing the amount of waste and providing sufficient nutrients and protein to the crew. Then, some basic considerations. If you want to make this successful on Mars, you really want to leave some room for error. So you want to compartmentalize all the population. So if you lose one population, you don't lose the whole batch. So that's really important, and that's what we do here with our production system. The environmental conditions are super important. Temperature is the key, but also there's other variables there. The cricket population you take to Mars, it won't last forever. You really have to replenish the gene pool so inbreeding doesn't become an issue. And it's about 2 years that you can maintain a certain population. Then you have to bring more populations from Earth, which just happens to be the time, the orbits go together, Earth and Mars. But in the distant future, for example, if you have different farms on Mars, they can, exchange populations and get away with that with longer periods of time and hopefully become independent of Earth with that regard. And then, of course, redundancy, as with everything to do with Mars, because the distance is so large to get supplies from Earth. Yeah, and then the automation side of things and just maintaining the cyclical system so you don't run out of eggs. That's super important. All right, but I think that covers the main topic there. Now I would leave some time for questions. Thanks.
Thank you very much. It was very interesting, very interesting. You had, I really do like that, just how you presented your system. It is exactly what we are also teaching our students, how to do this kind of presentations in a system with the interaction. So now it's a very good example that, even you are using the same ways that we are teaching them. So
okay.
Thank you for doing that. Now you showed that what we are teaching them is very, very valuable.
For sure, for sure.
Hey, I will just go around the room and show you which are which teams. Okay.
Okay.
So then we can kind of, you can see everyone. So like here in the front, we have the whole, oh no, wait, you are another team. So here, these four here are from Horus. And then he
Hello.
together there in the back with the Averes team. And in that other corner, we have the team. And here we have one representative of Terra Beta, right? Yes. So I would propose that like we go through the questions now. So the student could come here and ask the question so you can hear it, and then you can just start the discussion freely as long as you wish. Does this sound okay?
Yeah, I'm here to help. I'm in no rush.
Okay. So then the first question could come from Team Horus. So if someone could come, I have here your question here laid out. So yeah.
Okay. Hi.
Hello.
Thank you for your presentation. I at least enjoyed it a lot. Our question is or relates to the last year's team. How useful was the collaboration with Team Biomars to EntoCube, in your opinion? And if it was useful, do you think you would want to do a collaboration again this year with some team?
I mean, for sure. I mean, that's why I'm here. I definitely want to cooperate and do more research in this area. I would say this is more of a personal project than a company project right now, but I do have the resources of the company available to me and all the information. When it comes to last year's project, I would say, to be honest, maybe technologically there wasn't that much that we gained from it, but I think that's to do with that we didn't coordinate on our side that much. So maybe it was a new project, a new kind of program. We didn't know what we could gain from it. Now we have a better understanding, so I think we can coordinate better. And if the student projects there want to actually do a certain thing that helps with the commercial side of things here on Earth, then we can definitely help and kind of pinpoint you in the right direction there. And that would be really helpful to EntoCube. But I would say that personally, I want to just see that you guys are enthusiastic about it. You learn and take this space front forward in this regard.
Mm-hmm.
For sure. And if you, I mean, maybe the technology side of things wasn't that useful, but if you think about the big challenges of the industry, that's funding, laws, and then the technology and then consumer habits. I think we went a lot further with you guys with the consumer habits. So the guys, for example, did an event where they served crickets and other insects. So that takes the whole field forward, because we can figure all these different technology side of things, but if we can't convince astronauts to eat insects and people to eat insects and enjoy it, then it's no use. So the consumer habit side of things is really important, and getting used to this idea of edible insects.
Yeah, I agree. Well, thank you for that answer.
Thank you.
Robert, when we were talking with Tim Kopra, he was at the moment then at the International Space Station. If I remember correctly, I think Jesse even asked him what he thinks about. Now I could not recall the answer, but maybe if you're still in contact with Jesse, you could ask him that what was that. He had a very, very detailed opinion. So
okay, yeah, I'm sure.
Yeah, I could actually, if I meet Jesse these days. Jesse actually continued his own kind of a company, growing a company out of aeroponic food growing system. And even in Slush, they won some prize about in a competition about this rural environment improvement systems, these kind of things. So he has continued.
I gotta look up that, yeah.
Okay, the next question from Averes, please. Someone.
Hello.
Hello. How are you?
Fine, thank you. Yeah. So you mentioned that it is quite important to maintain the correct climate to farm insects, but how does it exactly affect their behavior, or is it just a metabolic thing? They don't eat so much, or so on.
Yeah. So thanks to your question, I added this graph. Let's go back to the graph. Let's see if we can make this work. So it was this one here. Can you see it?
Yep.
Okay. So yeah, the environmental conditions are the key. So they make it or break it for the entire thing. So temperature is the key thing. Here you can see kind of the effect of temperature. So yeah, if you're growing insects in room temperature, it's super slow. So from birth to the time we harvest, here you can see on the left that it takes maybe 120 days to get to that harvest stage in room temperature. But if you crank up the temperature up to 34 degrees, then you get the green line. So you get to harvestable age in about a month, and then you get a lot of harvest during the year. And if you look at the red line here, that's the case for the Southeast Asian farms that are just in open air. They don't control the temperature. It is whatever it is during that season. So the temperature varies outside, then the harvest times also vary. So you really want to optimize the temperature, and you want to control it. So then you get these predictable dates for harvests, and you can automate the process. You can collect the data when you have a really controllable system, and that's definitely the way to go. And also, not temperature, but also humidity is important. And what we can control is also the CO2 and the O2 levels. And then if you go really into the details, yeah, okay, if you have a really high temperature, then the fat content of the insect is higher. That makes it a little different to bake that into goods, and all these different small things. But those are details then.
Okay. Yep. Thank you.
Okay, next question could come from ET.
Hi. Which do
Hello.
you think will be the best insect to grow or farm in Mars? Like with the environment with harsh conditions that are suitable for consumption.
So the question was, what insect species?
Yeah. Which do you think is the best insect to grow?
Yeah, yeah, yeah. Like I said, you really have to think about. Okay, I will for this. I will go back to the slide with all these different things, so you can get an idea of what I'm talking about here. So the short answer is mealworms. I think mealworms is the way to go. We personally do crickets, but I would say it's more to do with mealworms. They're easier to rear. They're not so dynamic. Crickets hop around, they move around, a lot of moving parts. Mealworms are easier that way. They have other drawbacks, but I would go with that definitely. And when it comes to food, I think crickets and mealworms are the two options there, because when you go to the other different species that are eaten worldwide, you don't really have that much information about them. So they're, it can be like, I don't know, really, traditional eating habits and passed down from father to son, and you really don't have scientific information to back anything up, and how do you successfully rear them. But for these types of insects, you have that data available to you, and there are companies all around the world that are right now doing production systems, doing the research for these insect species, and that information can be applied directly then to Mars missions in the future. You don't have to reinvent the wheel. You definitely don't want to do that in the case of Mars. You want to, take all the different, things that can go wrong away, and go with what is known to work. And so you want to go with these mealworms and crickets for food, and then black soldier flies for feed, definitely.
Okay. Thanks.
Okay, then Horus one more time. Your second question.
All right, hi there again.
Hello, we meet again.
Has EntoCube thought of growing bees in space or in Mars? Because for us, it seemed that honey would be kind of appealing to astronauts.
I'm getting the sugar tooth already thinking about it. Yeah, I actually looked into that a little bit. Yeah, there's benefits of honey bees in orbit, just to do with pollination.
Oh yeah.
So that is another benefit of that. We don't know, we haven't looked into bees for space, and not even bees for Earth applications. But yeah, I looked into it, and in the 1980s, actually, there were some tests by NASA in orbit with bees, and there were some promising results, but it's a little challenging. And right now, I don't know what yeah, I don't have a good answer for you for that one. We don't have any, ideas of going down that route for sure.
Yeah, like honey would be, of course, good, but I have no idea if people eat bees here on Earth.
They do actually, yeah.
Okay.
It's one of the, I would say, top 10 species that are eaten for sure. And what is an option there is that we have, for example, one honey farm in Forsa who has proposed that we use their spent honeycombs as feed for the crickets and other insects. So that kind of circular economy system is definitely possible. And also we've talked to a mushroom farm who has these spent mushroom casings where mushrooms, grow, and then the spent casing are just thrown away into the field, but we can use that as feed. So there's that added option there as well.
All right. Thank you.
Okay, Averes. Maybe there could come also different people. Don't be shy. So Robert can see that there is more than two of you.
Yeah. Hello again.
Yeah, hello.
Martian greenhouse could benefit from lower atmospheric pressure. So, do you have any opinion how you could perhaps combine the living space for insects and grow space for plants in the same structure, or is it impossible to have insects in those lower atmospheric pressure conditions?
I wouldn't say impossible to anything at this point. It's just a matter of figuring out how. I mean, yeah, lower air pressure inside the habitat is good for two reasons, I guess. You need less air, and that if you bring air from Earth, if you produce more air, that's just more resources to do that. And also because it's a near vacuum outside, you really want lower air pressure inside, so the structures of the habitat can be lighter.
Yeah.
Those two are the reasons for that. But yeah, it's possible, and I would say they complement each other quite well, plants and insects. So the insects will produce CO2, and then that CO2 can be used by the plants, and the plants produce O2, which is then used by the insects. So those two balance each other out quite nicely. And I believe actually BioMars team did some tests with how much crickets expend to get CO2. So maybe you can access that information.
Yeah,
that would be super useful. I would not, in that kind of environment, put insects and plants directly in contact with each other. I think that's one takeaway here. So you have your insects in some space there, plants in other space, and make it controllable. But I would say it's possible. It's a matter of process. It's a matter of process, I would say.
Yeah.
How you design it.
Yeah. Thank you.
Okay, E.T.
Hi again. Well, actually, our original question has been answered already by your presentation, so we're going to change it. Okay, so what is your opinion in terms of harvesting, for example, mealworms? Like instead of consuming the whole mealworm, we'll just cut it in half and then consume the first half, and then the other half will just regrow it. Would you think that would be
Regrow it?
sustainable? Yeah.
Oh yeah. I don't know. The short answer would be that I wouldn't know if it survives. I, Yeah, I wouldn't say that. Maybe more of the approach that, eat half of the population, save half of the population, then to reproduce. I would say that's a more certain way of doing things.
Okay, that's it. Thanks.
And Horus had one more question. There comes now a different person, so.
Ah.
So hi, we noticed that there on your slides you did mention microgravity on insects, but what are like the more specific effects on insects of the microgravity?
Well, we don't know yet, I guess. That's the short answer. I mean, there's some research done in orbit with insects. For example, there's different kind of results. I mean, the insects behave differently when they are born in orbit in zero gravity and then are introduced into gravity conditions compared to when you take insects from, for example, Earth gravity conditions to orbit and then back. So there is definitely effects on gravitation deprivation on insects. But I would say that the 40% of gravity on Mars is close enough to Earth that we can, make conclusions based on what we see here on Earth with the system we developed. I would say definitely. So that's why I feel that it's so promising that we can develop a system here on Earth. It can function here as it is, and we can take that system and directly implement it to Mars because the gravity conditions are such so close enough. I would say close enough. And if you want to take the biggest variable, the biggest difficulty away from this whole equation, it is that you don't want to start figuring out how to rear insects in space, in microgravity. That's going to be a whole different ball game. That's going to be super difficult. So that's why the suggestion that you take the eggs for the trip and just forget about the rearing in space stuff and take the eggs and let them hatch in the gravity conditions.
Okay, thanks for your answer.
These were all the questions from the list that we have, but if you guys have some other questions now that you saw the presentation, or is there anything you're interested in? So there was a question if they could have the slides that you showed.
For sure.
Yes. Is there any research about earthworms instead of mealworms in space?
In space, you mean?
In space, or even as an edible earth food
I mean,
source?
for sure. When it comes, look into insects in space. Google that. There's some existing. Okay. So there's the Chinese Space Agency actually did this research project where they had, I believe, 3 taikonauts strapped into isolation chamber for 2 or 3 months, and all these taikonauts had to eat was the plant crops they produced, and then the mealworms they produced with plant crop, inedible parts, and all that jazz. So they did this essentially, this system. They made it work for 2 to 3 months. So it's possible, definitely, and I would say that's an interesting project you could look at, how that worked with mealworms and plant crops.
I was wondering, maybe you could tell, because insects are something that is so, we are not used to, right, eating them. So would you feel comfortable telling a little bit about, so how much would it cost to actually like buy insects, or how much someone could actually earn by producing them here on Earth?
So I mean, the cost structure is a tricky thing. So it's really manually intensive right now. So it's pretty much done by hand entirely. In Finland, the price that we have for crickets right now is about 80 euros per kilo. And with technology, with automation, with production solutions, and scaling up, we're trying to push it down to maybe, well, definitely under 10 euros per kilo. I want to say 5 euros, somewhere there. But that will take automation. And in the case of Mars, I wouldn't put too much emphasis on kind of the price or the level of automation. I would just look at the cost benefit analysis there, and kind of what makes life easiest for the astronauts on Mars. Then when the time comes to kind of take care of the insects every single day, and what are kind of the bottlenecks where things can go wrong and where human error can kind of mess things up and just spoil the entire food source if something goes wrong. But yeah, it's a consideration, the price here on Earth when you do it commercially.
So yeah, if someone wants to start a business of growing insects, now is a good moment, right? When it's not automated yet.
Oh yeah, I mean, we really want to see more entrepreneurs in this area. We need more, companies starting new things, and I think it's like the new gold rush. People from all different backgrounds are coming into this area with these wild ideas, and it's kind of exciting that way. There is no school to go to be an edible insect entrepreneur, not yet. So all different backgrounds are welcome.
Okay, there is a question now.
You mentioned that was it Sirkkabutti or something like that?
Mm-hmm.
So is there a way for me to go into a shop somewhere in Finland and buy that?
Oh yeah, so there's now 4 shops you can walk into. There's Ruohonjuuri in Kamppi, Helsinki, Ruohonjuuri Tampere, and then there's Punnitse et Säästä in Tampere and Helsinki. But I guess you're in Joensuu, so you can order online from Ruohonjuuri. That's where you can get it from, or delivered to your doorstep.
Well, I'm actually visiting Helsinki this weekend, so I'll definitely.
All right. And I think tomorrow or the day after, it's coming to hyvinvoinnin.fi also. And there's other stores are lining up to get it.
That's good.
So I would propose maybe, now the students have seen your presentation and you now met. So maybe the communication can continue in a way that when the teams are ready with some proposals, they could reach out to you, or how do you see this?
Yeah, so definitely I'll be available. You have my contact information, I can resend them to you. There's certain things that I can kind of suggest that of course there's the angle that if you want to, try freezing eggs, doing the smart stuff, doing applications for Mars, but if you want to go the road that whatever you're developing also can have some commercial applications here on Earth, I can suggest a certain list of things that would be really valuable. So that could be another approach. So I can do a list of things that would be interesting in both regards, for Mars and commercially here on Earth. And you can choose or not choose, or do where the interest goes.
Sounds very good to me. How about you? Okay. Thank you very much one more time.
Well, thank you. Thank you.